The following is the video solution from JSDT Solutions. Question 9.1 says, in the diagram below, PQ is equal to QR, which is equal to RS. And we're also told that VR is parallel to TS. Okay, the first question, 9.1.1 says, determine the value of TV over VP. Okay, so since these three sides are equal, we could just call them A. Okay, so if that was A, and that was A, and that was A, because they're exactly the same, how would we find TV over VP? So using the proportionality theorem, because we have a line parallel to one side of the triangle, what we can do here is we're just going to pair it with the side that it is in proportion with. So that's going to be RS over PR. And you see how PR is made of two sets of A's added together. Okay, so here's what we can tell them. We can tell them that TV over VP is equal to, and so that's going to pair with RS, or we can say SR over RP. So SR over RP. And the reason for this is because we have a line drawn parallel to one side of the triangle, or we could also say proportionality theorem. Okay, so that is what we have. And so therefore, TV over VP is equal to, now you see how that's A, and then that adds up to 2A. If you said A over 2A, what does that simplify to? It's going to simplify to, when the A's cancel, it's just going to be 1 over 2. So that's exactly what this is equal to. Its ratio is 1 over 2. And that is our answer, and that is our reason. And moving on to 9.1.2. So question 9.1.2 says, determine the value of the area of triangle PQV over triangle PST. Okay, so let's go ahead and highlight those triangles. Okay, so looking at the triangles that they asked for, also just remember that we were able to show them that TV over VP was equal to 1 over 2. So looking at those ratios, TV takes the 1 part. You can call that another letter. You can call it B. And then VP takes 2 parts. So we can call that 2B. Okay, so we're only going to use their ratios. We don't really care about the letter for now. We'll just use their ratios. It's really just to differentiate between a length and a ratio. Okay, so since they say PQV over PST, PQV is this triangle over here, PQV. Okay, so that triangle. And then PST is the bigger triangle, as we can see, PST. Okay, so how will we find their areas over each other? Well, we definitely cannot use a half times the base times the height because we don't have a perpendicular height in both triangles. However, we can use the area rule. And with the area rule, you're going to have one single angle. And it would work if both triangles have that common angle. And we can see that in this case, that is angle P. So in order to find these areas, okay, the ratio that they give us, we will say a half multiplied by the side. Okay, so we're looking at this triangle on the top. That is this one over here. And we're going to say a half multiplied by PV multiplied by PQ and then times sine of angle P. Okay, so a half multiplied by PV, we can just start by telling them that times PQ times, or you can just say sine of angle P. And this goes over a half multiplied by, and now we're going to use the sides of this bigger triangle. So that will be a half multiplied by PT multiplied by PS, and then sine of their center angle, that center angle. So we'll say a half multiplied by PT multiplied by PS, and then sine of angle P. And so here's the thing about it. Because angle P was common in both, they will cancel. And so this is really just equal to, and the halves will also cancel. So PV multiplied by PQ, PV, we'll see that as a ratio of 2, multiplied by PQ, that's going to be a ratio of 1. So we're going to just say these cancel, and we're saying we have PV as a ratio of 2. If you like, you can call it 2B and you'll just see how it would still cancel at the end of the day, okay? So if it was 2B and we said multiply by PQ, which we saw was just 1, or we could just say A, and then this goes over PT times PS. So PT is that entire length, which you can see is 2B plus B. So that's 3B. So 3 as a ratio. So we could say 3B multiplied by, and PS is this entire length, which will be the A plus the A plus the A, which is 3A. It's a ratio of 3. Okay, so looking at it like this, you see that the letters would still cancel because these are just ratios, okay? So when they cancel, we really just have 2 times 1, which is just 2, and then 3 times 3, which is 9. So that is 2 over 9. The ratio of these areas just equal 2 over 9. And that is our answer. Question 9.2 says, in the diagram below, B, C, and D are points on the circle. And then we have that ADC is a straight line. AB is a tangent to the circle at B. Okay, so that's going to be an important point. This is a tangent to the circle at B. And the first question, 9.2.1, says we need to prove, given reasons, that triangle CBA is similar to triangle BDA. Okay, let's highlight those triangles first. So CBA, from C to B to A, is this triangle. And then BDA is BDA. Okay, so we can already see from this that they are sharing an angle, angle A. So we already have 1 in the box. We have 1 equal in both triangles. And then the only other thing to use is this tangent they gave us. So let's use that. The angle between the tangent and the chord is equal to the angle supported by that same chord. So there we go. In the red triangle, we have angle B1 being equal to angle C. And then by default, the other 2 angles will be equal. Okay, so let's go ahead and name our triangles first. So we'll just tell them in triangle CBA and triangle BDA, then we have angle A being equal to angle A, and this is because this is a shared angle. So it's not something we have to look for, it's just already shared. And now we have that, and we can tell them that angle B1 is equal to angle C. Okay, so we can tell them angle C equals angle B1, just following the same order of putting the blues first. So angle C equals angle B1, and we can tell them that that is because of the tan chord theorem. Okay, so because the tan chord theorem here is true, those are equal. Okay, so because of the tan chord theorem, and then by default, because these 2 are equal, the third angle in each triangle will have to be equal. So that means that angle D1 is therefore equal to angle B1 plus B2. Okay, because that is the entire angle, that third angle of the blue triangle. Okay, so it means that we can just call this angle ABC. So therefore, angle ABC is equal to angle D1. And you can either say third angle in a triangle or the sum of angles in a triangle. Okay, so now that we have that, we can finally just conclude that therefore this means that triangle CBA is indeed similar to triangle BDA because we have 3 sets of equal angles in each triangle. And that is our answer. Moving on to the next question. Question 9.2.2 says we need to prove that AD times DC equals AB squared minus AD squared. Okay, so let's just see how these relate to the sides we have in our triangles. Okay, now because we already proved that these triangles were similar, we can just use their proportions because they still refer to the sides that we have. So let's use these proportions and just see how we can, instead of looking at the diagram, let's just see how we can actually form this using these proportions. Okay, so since we know that these 2 triangles are similar, how can we form this So it includes AD, DC, AB squared, and AD squared. Let's see what we have here. Well, do we have AD? Yes, we do. Okay, so this side over here, if you take these two, the second and the third letter, and you also have to take the second and the third letter here. So that would form BA, or we can just call it AB, over, and then DA, or we could just call that AD, is equal to, and let's just see, which other side do we have? DC is not here, so we'll hold off on that so long. But we do have another AB. Okay, so it's probably where the squared is coming from. So we have AB, and then we would have to take that with AC. So we can just tell them AC over AB. Okay, and let's see where this goes and see whether we can actually reach this or not. Okay, so when we cross multiply, we're going to get, and of course, when using these proportions, we'll tell them this is because we had similar triangles. Okay, and you can just state the triangles that were similar. That was triangle CBA was similar to triangle BDA. Okay, so now let's cross multiply here. So that's AB times AB, which gives us AB squared. And then we have AD times AC. So now looking at what we have in our question compared to what we have here, we've got AB squared of an AD, just one of it. And then we don't have DC, but we do have AC. So now our focus can be on AC. AC has to be some sort of line that helps to somehow include DC. Okay, so let's go ahead and look in our diagram and see what is AC. Okay, so AC is this entire length. And do you see that AC is made up of AD plus DC? That actually makes sense. So let's actually note that down. We'll say that AC, but we know that AC is equal to AD plus DC. So in place of AC here, we're going to substitute this. So long, our equation is now AB squared is equal to AD multiplied by, now it has two terms, so we'll open up a bracket, and so we're saying AD plus DC. Okay, and then we can just multiply in. Okay, so you see where that AD squared came from. So it means that AB squared is equal to, so this distributes in and becomes an AD squared. That distributes in and becomes DC. I just want to put it in their order. Okay, so it's AD times DC. Okay, AD times DC. And now all they did was made this the subject. They just made AD times DC the subject. So we'll leave it here. So AD times DC is equal to, and transpose the AD squared. So we have AB squared minus AD squared. And there we go. That's what they have. Okay, so just writing it like that. Putting this on the left and this on the right. And that is our answer. And that is how we prove that. Okay, so that is it for question 9.